So this is my viewpoint of the James Webb Space Telescope. This message appeared from Steve yesterday, but I would like to point out that the lecturers at the Royal Institution are given more than 24 hours notice that they have to prepare a lecture previously undelivered to explain things to people of widely varying backgrounds. So I thought it wouldn't be very entertaining if I just went into explaining what I did, and you wouldn't understand it without the context. So my plan is to start with what happened on the with regard to this project on the Christmas Day, and what should happen next to the James Webb Space Telescope, and that will lead to describing the major elements that make up that telescope, and then we can focus down onto the little bits that were my personal involvement. I hope that'll be okay. I hope I can control it as well. Right, these guys are under a heck of a lot of stress here because about $9,000 million worth of equipment is under their control as they're about to launch it into space. And if some of that, this is the guy who is ultimately responsible for it all and has to decide whether it all goes ahead. Jean-Luc Voyer. Unfortunately, the American commentator described him as Jean-Luc Voyeur, which doesn't mean quite the same thing. Anyway, this is all in French, the speech here, but this video is silent. He's just said "toc" for 7 minutes to go, and they're really committed, unless there's a major fault now, to go ahead with the launch, which I shall now attempt to skip ahead a bit more. That's 1 minute to go. He's just said cleared, and everything is fairly automatic from here. This is a distant view of the rocket here, and it's surrounded by these strange things that look like sort of World War II radar aerials or something, and they are lightning conductors, just in case you don't want 300 tons of high explosive and $9 billion worth of equipment to get struck by lightning. Now we're approaching, we're into the last seconds of the countdown, and the next thing we see after this close-up of the nose cone, which contains the actual satellite that's to be launched, we see the coolant couplings to the base of the rocket, which will disconnect a few seconds before it goes. There we go, those disconnect. And the next stage is the ignition. Now we've got the ignition happening of the main thruster, followed by 7 seconds later by the main solid rocket boosters. And off she goes, lighting up the sky, shaking the ground if you're there on site. Quite splendid the way it lights up the clouds, I think.
Where does it take off from? Where is the rocket base?
That's a good question. It's in Kourou, which is in French Guiana, in which I didn't realise there's a French colony in South America. I thought it was all either Portuguese or Spanish speaking, but there is a French little former colony or present colony there. Where this is launched from. And the big benefit of that, compared with almost all other launch sites like the Russians and so on use, is that it's practically on the equator, which gives you a big help with an initial velocity. Now we're into a simulation view. Down at the bottom here in the bottom left corner, we can see the speed, the height, and the distance traveled. The graph shows a green line, which is the planned trajectory, and a yellow line, which is the actual trajectory of the craft. And then we've got an artificial 3D simulation of what it would actually look like if you were in a position to see it. And we can see Mr. Voyer here, who from time to time, he's the only person who speaks live in the control room. From time to time, he announces that this, that, or the other has happened. The next thing that should happen is shown on this graph. This little point that's marked is where these solid rocket boosters burn out and are discarded. One important thing here for them is constantly to minimize the weight that they're trying to accelerate and launch. So you discard anything you don't need as soon as you don't need it. We're just coming up to that point now. Doing, there they go. And a few seconds later, that's confirmed by the mission controller. The thing we see on the middle picture here down at the bottom is the telemetry, where the radio signals to and from the rocket are being received and sent from. And the first stretch is done from the launch site, more or less. Then the next section is done from a base in a place called Natal in the extreme east of Brazil. After that, it moves on to a mast in Ascension Island, British colony in the middle of the Atlantic, before moving on to Libreville in Africa. Now we're about to see something that rather surprised me. Here's this rocket shooting into space with immense acceleration and velocity. And what do? They throw away the cover from this highly delicate piece that's mounted on the front of it, with the whole thing they're launching. Now they're out of the atmosphere. It no longer needs that protection. And there it goes naked, so to speak, from here on. And this is the view from inside the launch vehicle, looking at the telescope. There's quite a long time delay on this, so we actually see in this picture the moment when what we just saw in the simulation in real time happens. So that there suddenly daylight is falling on the actual telescope as the nose cone is discarded. So now I want to zoom ahead a bit more. After a bit, the big rocket that we saw has now been dropped, and we're just into the final stage of the launch rocket, which is ignited and is taking us further on. And an interesting thing is, if you look at the altitude graph here, it's now dropping. This is something to do with getting a gravity slingshot effect, which I don't claim to understand, but they're able to improve the speed and distance of the launch by dropping a bit at this stage in proceedings. If I now skip further ahead, you can see now it's picked up and is now heading really high upwards. We're now 600 kilometers above the ground and 23 minutes into the flight. I'll move a bit further on, 25 minutes into the flight now, and we're heading for the next landmark in this graph, which is separation, where the space telescope becomes independent of the launch vehicle. And these guys who've been responsible for it so far, their responsibility is almost at an end. At this stage in the flight, it stopped burning its engine, but is making very slight adjustments to try and ensure that the satellite here is not rotating or anything, so that it drifts off perfectly unperturbed, because any further adjustments mean using the fuel, which is a limited resource, which is what will cause this eventually, if everything works perfectly, it will still stop working after between 10 and 15 years when it runs out of fuel. So saving fuel is absolutely one of the highest priorities with this. And now we're coming up to the moment of separation at 27 minutes. So that happens, and it's a fairly magical moment as that goes away. A thumbs up from the Director of Operations, and there's quite a lot of people rather overcome with emotion in the control room. Actually, they haven't quite finished, because they now have to do an avoidance maneuver to make sure there's no possibility of this launch vehicle colliding with its payload afterwards. But that is pretty much the launch completed. There's one more bit just coming up, which is really good, which is the actual camera shot from the launch vehicle of that separation happening. There it goes, drifting away from the rocket. And this, as they say in the commentary, is quite a poignant moment. This is very likely the last time any human being will ever see the James Webb Space Telescope. From now on, it sends back information, but you never get a view of it from outside. So a lovely picture there with the Earth in the top of, and the telescope floating away beside it. And we also get rather ahead of schedule. This bit is now controlled from a different control room in Baltimore in the USA. And with it apparently functioning correctly, they waste no time in deploying its solar cell arrays, which caught the official commentators by surprise. It was quite a while before they noticed that this was happening. But there you can see the solar cell arrays being deployed from, so now it's able to acquire power from the sun rather than relying on its batteries. So at this stage, that took place at 12:20 Greenwich Mean Time on Christmas Day. So by 1 o'clock on Christmas Day, JWST is launched into a very wide elliptical orbit around the Earth. In fact, it will never be returning, as I'll explain later. It's got its solar cells deployed, but all the rest, you could see that was a fairly oddly shaped object, and the whole thing is folded up and inactive. And it's going to take them 6 months, if everything works perfectly, to get everything up and running. When it is fully deployed, it should look like this, with the main telescope bit up the top here, a big lot of sunscreens to protect it from the solar radiation and from the heat, and the various works, particularly its thrusters down the bottom that will maintain it in position. So it has to unfold and deploy all those bits. Firstly, the communication dish, then the sun shield, then the main mirrors. Then it carries, it will be, once it's got the sun shield deployed, it will cool down, which, as I explain later, is extremely important. then they can start testing the instruments properly. And all this time it's moving out. This is rather a good picture, actually, which I found after I'd done that slide. So we just got to this stage just near the Earth of solar array deployment. Then it will deploy the communications antenna. It may make maneuvers to adjust its trajectory. If the sooner they can make any adjustments to correct its trajectory, the less fuel they have to use to end up at the right point at the end of the mission. This ellipse here that it passes, that's the orbit of the Moon. So that's it gives you an impression of how far that is. It's going to end up 4 times as far away from the Earth as the Moon is. And on the way, it will be deploying that sun shield and the main mirrors. This slide is intended to explain where it's going to, although the proportions are hopelessly inaccurate. Where it has to end up is one of the Lagrange points. There are 5 Lagrange points. These are places where you could, in theory, if everything balances out perfectly, you can remain with the forces of gravity and the forces of your, the centripetal force of your orbit, all balanced out without expending any energy. And we're in a fixed relationship to the Earth. So one of these is where you're on one side of the Earth and you've got the sun pulling one way and the Earth pulling the other way, and the force needed to keep you on your orbit. And that's the L1 point. And James Webb is heading for the L2 point, where both the Earth and the sun are pulling in the same direction. But the fact that it's on an orbit further out means that it can benefit from that pull to keep it actually aligned with the Earth. So it remains in sight and on the shadowed side of the Earth permanently. In fact, it describes a little orbit about that L2 point. And to explain a little bit what it is supposed to end up like, it's a reflecting telescope. So it has a big primary mirror which collects the energy coming from the left in this picture, collects the starlight, which in theory you could look at from this point, the prime focus, but that would put you right in front of the primary mirror. So it's almost always more convenient to have a secondary mirror, which then sends the image back so that you can look at it in the same plane really as the primary mirror, through a hole in the primary mirror. That's just to explain what we're aiming to achieve in the way of a telescope when it gets unfolded. Down the bottom on this picture, it shows you a somewhat better image perhaps of the distances involved. So we've got the Earth here. You can see what the orbit of the Hubble Space Telescope is, a mere 580 kilometers above the Earth's surface. The Moon is considerably further away. The farthest any human being has ever been is apparently Apollo 13 going around the far side of the Moon. And Webb is going to be 4 times as far away as that, about 1 million miles from the Earth. So service visits are not expected to be practical. Everything has to work first time. Right, you can probably see a time scale that I can't see in the top of the picture. This is the first stage of deployment of the sun shield. It extends that big tray on one side of the assembly. This is it all unfolding now. You can see in this view, the sort of main body down the bottom of the object. You can see this solar array here. I'm hoping you can see where my pointer is as well as the actual picture. And it's unfolded this. Next it's going to unfold the other side of the array, which is of the solar protection. Then the main telescope part moves outwards a bit to allow space for this sun shield to deploy. And then this rather Heath Robinson arrangement of stretching out the sheets of the sun shield. This is all, although it looks very crude, is the product of amazing amounts of research and the development of coatings and the fabrication of these sheets, as well as the method of deploying them, has all been is the fruit of years of research work. So now they're stretched out, and there are 5 layers which then have to separate to provide the necessary shielding. Now we come to the actual telescope doing things. Here, right in the middle, you can see the secondary mirror, which is just unfolding at this point. It's gone on 2 fixed legs and 1 folding leg to come forward and be deployed straight in front of the primary mirror here. Primary mirror is made of a number of hexagonal segments, which I also nearly got involved in the manufacture of. One of our machines made a prototype segment for the primary mirror, but they eventually decided on a different technology from that prototype, so it went to another firm, and that's not the fruit of my labours. Then another bit of the telescope unfurls, and now the last 2 parts of the main mirror. So this mirror is 6.5 meters diameter. So that's quite a big telescope, even if it were on ground, and far, far bigger than the Hubble. And at the bottom, we've got, you may have been noticing, there's a view of where it is in its flight path with the Earth and the Moon here. Then I'll go to 2. So now now we come on to the instruments. These are the bits that actually collect and process the data that's reflected back from the secondary mirror here into this compartment, if you like, in the middle, right behind the main mirror of the telescope, the focus point that I described. These are the instruments. With this one here is the one where my bit goes, the NIRI. I think that's all for that. Then the other thing I wanted to show you from this video is the effect of the sun shields. It's a vital feature of, this is an infrared telescope, so it's looking at wavelengths that we perceive as heat. And it's looking at extremely faint stars. It's trying to detect the heat from really faint stars, fainter than any we've ever seen before. And that means it can't have any heat. It can't be receiving any heat from the sun or from the Earth or from reflected off the Moon and so on. So the heat shield is of vital importance, and the fact that the other side is effectively exposed to interstellar space means it can radiate away a lot of heat. So when the sun's shining on it, the hot side will be at 85 degrees Celsius, almost boiling point. Whilst the cold side will be at minus 233 degrees, only about 40 degrees Kelvin. But the instrument that I've been involved with, that's far too hot for it. It's looking further into the infrared, and it has to, in addition, have a refrigeration unit to bring it down to only about 6 or 7 Kelvin, around minus 267 degrees Celsius. So there's the temperature business is quite a vital element. So here's a list of the instruments. There are 4 main instruments on the telescope, of which 3 are described as near infrared, and the MIRI is the mid-infrared, looking further into the red side of the spectrum. Red is quite good for these very distant observations. Apart from having some other ease of manufacture of some of the parts, from our point of view, but from the purely scientific point of view, very distant objects are red shifted so that you want to look further red into the spectrum to observe them. This is just a diagram of the assembly of all the instruments. So MIRI, the mid-infrared instrument, is on that side, and near-infrared ones in other places. The MIRI project was or is a European one, with the principal investigator led from the UK Astronomy Technology Centre. Gillian Wright, this is her own slide, was the principal investigator. And the MIRI instrument is unbelievably complicated for something they expect to work unattended. This is just showing the path of the light. It comes in here and gets split in various directions and bounced off all these bits and pieces. It goes through filters all over the place and ends up shooting out to IFU2, IFU3, IFU4 and IFU1. Which is where my bits are to be found. And I also showed this overview of the MIRI instrument from the Arizona University, which has a huge astronomy interest because it actually mentions image slicers. The image slicer is the bit that I was responsible for making to some extent. Here it is in its assembly. The light comes in from the bit we've just seen onto this device, which I've sent you a picture of previously. We'll see the other side of it. And that sends the image into down all these holes, basically, in bits, onto another set of mirrors, which we also made, and bounces off a flat mirror and out through these slitlets to the sensors and spectrography department. This diagram shows a bit more of what it does. So you have an image of some stellar object comes in and hits the slicing mirror, which is my bit, which sends slices of the image out, and you can see down the bottom here the way the picture at the top has been divided into strips. Now, the reason they want to do this, because they don't simply want to look at a picture like this. They want to look at a data cube, which is built up of not only the X and Y spatial coordinates of a picture, but also of information about what wavelength you have in each of those XY coordinates. So that's why they call it a data cube. you've got an X and a Y and a wavelength cube. But the sensors, of course, are only two-dimensional. So they have to split it up first into stripes before they can rebuild it as a cube of information. So here is what a picture might look like. Along the slice, they will take a number of samples, and for each one they will do a spectrograph and get an idea of what the color combinations are in that area, and they can plot them in this three-dimensional manner that I've just described. So spectrography for astronomy purposes, we've all seen this picture of the way you can split up light into colours. And this is one of the most powerful tools that astronomers have to know what elements there are in gases and in stars. They can see what the combination of colours are within the light that comes from stars, and that would tell them what there was in the emitting source, and also they get black lines where there was something in the way, which will tell them what was in a gas, for instance, that was in between the thing they're observing and the telescope. So this is a very powerful tool, and this ability to combine geometric and spectrographic information, which is only possible because of the image slicing, is an extremely powerful thing. They can do this now in a single picture, whereas previously they would have had to do multiple shots to get that information, during which time things might have moved or changed. But I didn't know anything about any of that back in 2003, 2004. I just got this document on my desk and some drawings, which were very weird and difficult to understand. And Professor Paul Shaw from Cranfield University said to me, "Could we make these with nanocenter?" This is nanocenter, which is a very high precision lathe that we made and which was still being operated by the university at the time. And in that document, there were these pictures of what they were actually looking for in the way of components. And when one started looking at the drawings, one discovered how very small these were. And there's only about 12 millimeters wide, these things. Each of these stripes, which is the critical bit to manufacture, only 1 millimeter wide, with a specific geometry. And these are the complementary bits which I mentioned when we were looking at the assembly picture. So we actually made these bits as well, but they're slightly less spectacular, so we tend to show pictures of this one more. But you actually have to make twice as many of these because you need one of these to match each side of this. Having split up the image, then this one refocuses it back to the spectrometer. And we have this kind of diagram to show this shows the center of the spherical surface that has to be produced on each of these stripes. So we have 11 stripes. This is half of that mirror assembly. And the centers of the center of the sphere, number 11, is up here when you look in this view. They're all in a row like that, which really defines the way that the image will be spread out to land on these bits in a straight line, as we can see there. So that manufacturing was not obviously very straightforward to make these very narrow but accurately defined curved surfaces. And from my point of view of understanding what on earth the whole project was about, it was further obscured by the fact that they asked for ones like this and so on with no explanation as to why they wanted them, and other ones with different numbers of stripes, of the narrower stripes. And it turned out that this one, which had one wide spherical surface, was because that was a size they could actually measure whether we'd done it right or not. These other parts, they would only be able to test when they'd finally assembled the whole lot together to see, and then find out whether they got the image right or not. Well, I won't go into the technical details of the specification and so on, but the manufacturing process involved making this big piece of tooling which would turn around on the lathe and would hold the workpiece here. And for each of those spherical surfaces, as well as programming the movement of the cutting tool, this piece would have to be shifted by the operator, actually putting some gauge blocks under it to move it sideways slightly, so that the center of that part to be machined lay on the center of rotation of this lathe. This is what gauge blocks look like. These are very standard piece of workshop equipment, but they're extremely accurately made blocks of steel, so accurately made that you can put two together and they'll just stick to one another, and you can assemble any height you want by putting a stack of these together. And we use those to reposition this a little bit sideways each time we needed to step it to another position to cut the next stripe on the mirror. So there is one of the test pieces made in 2004 with the wide spherical surface for them to be able to check whether we'd done that one right, even though they couldn't verify the other ones so readily. And that's the most complex one. I got it wrong in the WhatsApp. There are actually only 10 stripes on one side and 11 on the other, so it's a 21 segment piece. And one of those is on its way out to Lagrange Point too. So these parts were made using the method that I devised. The tooling mechanical design was done by my colleague Mike Evans, who tragically died of a stroke, aged only 61. Just went home from work one day, and the next day his wife rang up and said he wouldn't be back. Anyway, the people at Cranfield University who actually did the machining work, I have to take my hat off to them, because it was, you can imagine repositioning those things for every one of those stripes, getting them all exactly right, and all with lots of other things to get perfect in terms of the temperature control of the machine and measuring the exact position of the cutting tool and so on. Immense amount of labour. But the parts that we made just came out right first time, as soon as we got the method sorted. And that was back in 2004. I think the last ones were delivered in 2005. The European contribution of the MIRI was finished and delivered to NASA in 2012, on schedule for the planned launch in 2014. Here it is actually being assembled into the satellite, the MIRI object. As you can see, it's a nice photograph, but you can't see anything about what it does. There's a couple more photos of the assembled telescope mirror. This one on the right gives a better impression of what size it is, with the men standing around. Couldn't get a picture of it actually fully deployed on the ground, so the artist's impression is the best finished view that I have. And that's it.
And Richard, you talk about being spherical. So each stripe is a little. If its shape was extended, it would be a sphere. Is that?
That's right. Yes, 162 millimeters. I'm not sure it was diameter or radius. I think, yeah, be radius. That's right. So they're all the little bits of a sphere, all with different centers.
Oh, that's 160 millimeters, right?
Yeah.
Uncle Richard, do you know specifically what your path is going to be pointing at? What conclusions might we get from your work?
Well, not really. It's got 10 years of astronomy so it's going to be looking at distant stars and galaxies. I guess the headline thing is, because it can look so far away, it's looking very much closer to the Big Bang, because the objects from if an object is a million light years away, that's a million years back in history. So and we're talking thousands of millions of light years, incredibly distant objects. So you'll see stuff much closer to the formation of the universe.
Cool.
But other things too. There should be able to find stuff like exoplanets. They're hoping to be able to, with the spectrographic analysis, find more information about the atmospheres of exoplanets, planets around other suns, things like that too. So it's not all the ultra distant stuff. But having it in space means they can see a much wider range of wavelengths than because a lot of stuff is absorbed by the atmosphere on Earth.
Yeah.